Okay, so we are continuing problem 1617 from the textbook, and we calculated the moment caused by both the distributed load and point loads. We use that to find the section modulus that is required to resist that moment, and based on that plastic section modulus, selected a W21 by 50, and then found the additional moment caused by the self-weight of that 50-pound per foot beam. And we saw that that didn't really add a whole lot of additional section modulus requirement, less than 2 inches to the third. So we went from a requirement of 93 up to approximately 95, which is still far less than the 110 provided. So it looks like we've got a good beam here, at least based on bending stress. So now we need to make sure that it doesn't deflect too much. So the deflection requirement, well, I guess it doesn't give us a deflection requirement for this particular beam. Let's go back to the book and see if there was a general deflection limit imposed on this problem. So I looked at the textbook, and it actually doesn't impose a deflection limit. But checking deflection is something you will need to do on the test. So I'm going to say that the deflection for this particular problem needs to be less than L over 240. That's a pretty common requirement on any kind of beam. So L over 240, the span here is 24 feet. And if we multiply that by 12 inches per foot, that's going to convert it into inches, and then divide that by 240. Let's see what that equals. That is a deflection of 1.2 inches. So what we're saying is we don't want the beam to deflect or sag more than 1.2 inches at its midspan. So there are a couple ways to approach deflection. We could solve for I and then go to the appendix and find a wide flange that has an I, or moment of inertia, that's large enough. The other thing to do is, if you've already chosen a beam and it has an I value that we've already looked up, and we have done that, we've chosen a W21 by 50, and it has a moment of inertia of 984 inches to the fourth, we could just plug in that moment of inertia and double check and make sure that the deflection is less than 1.2 inches. So if we go back up here and look at the beam diagram, remember that we had two different types of loads. We had a distributed load and we had point loads. Each of them are going to cause deflection. So in order, plus we have the self-weight of the beam, which is evenly distributed. So to figure out the total amount of deflection at the midspan of this beam, we have to add those deflections together. So I'll start the equation here. The deflection equals, so again, if you don't have these formulas memorized, you can look them up in Appendix H. So here we have the uniformly distributed load on a simply supported beam. The maximum deflection is 5WL to the fourth over 384 EI. So that's 5WL to the fourth over 384 EI. And then we also have the maximum deflection caused by the two point loads that are symmetrically placed on our beam. So our deflection max here is all of this. Again, this is a common mistake I've seen where students only include the first part of this equation, but it's the entire formula here. PA over 24 EI times 3L squared minus 4A squared. So I have to include all of that. So the deflection caused by the point loads is going to be PA over 24EI times 3L squared minus 4A squared. So I'm going to come down here to another line here because this is going to fill up some space here on my screen. So this is 5 times W. What is the distributed load? Well, the externally applied load was 1 kip per foot, but we also had a self-weight of 50 pounds per foot. So that is a total of 50 pounds per foot. If we convert that to kips per foot, for every 1,000 pounds, there is 1 kip. And so we're going to move that decimal place 3 times. 1, 2, 3. So it is 0.050 kips per foot. That's the self-weight. So if we add that to the 1 kip per foot, I've got 1.050 kips per foot. Now, things like E are going to be given in KSI. I, moment of inertia, is inches to the fourth. So I want to change my kips per foot here to kips per inch. I definitely want to be using inches as my unit of length, and that's really important. That's probably one of the most common mistakes I see with these types of problems is just not using the right units. So we always have to be really careful of that. I think it's good practice to write them down so you can see them and be reminded of what units you're working with. So I'm going to have to convert this. The feet, this time this is kips per foot. This is not a moment. This is a distributed load, W, so it is kips per foot. Feet are on the bottom, so to convert, I'm going to put it on top. For every 1 foot, there are 12 inches. So I'm going to divide that by 12 times my length. Again, this is going to be 24 times 12, converting it into inches, to the fourth over 384. E, the modulus of elasticity of steel, is 30,000 KSI. And the moment of inertia of the beam we chose was, we chose W21 by 50, and I wrote down the moment of inertia here, 984 inches to the fourth. So come down here, that's 984 inches to the fourth. Okay, so that's just the first part of the equation. That's the deflection caused by the externally applied distributed load and the self-weight. Now we need to add to that the deflection caused by the point loads. P, the magnitude of the point load, was 20 kips. So I've got 20 times A. A is the distance from the support to the applied loads. That's our 8 feet. Times 8 feet. But again, I want this to be in inches. So I'm going to have to multiply that by 12 inches per foot. So that's PA over 24 times E, 30,000 KSI, times I, 984 inches to the fourth, times 3 times L. The overall length was 24. But I want that to be in inches. So I'm going to multiply that by 12 and then square it. So it's just the L that gets squared, not the 3. So 24 times 12 will get squared, not the 3. Minus 4 times 8 times 12 squared. All right, so I know this is a long equation. You do not need to put this all into your calculator at once. You can break it down into smaller pieces, but in the interest of time here, I'm going to pause the recording and then calculate it all at once and reveal my answer. So let's do that. All right, so I just did the first part of this equation here, the deflection caused by the distributed loads, and I got 0.266. And now I'll calculate the second half of the equation. I am getting 0.574 for the second part of this equation. So I add those two together. All right, and I'm getting 0.84 inches is the total amount of deflection at midspan of this beam. Now, if our deflection limit was L over 240, or 1.2 inches, then the beam we have chosen is going to deflect less than that. 0.84 inches is less than 1.2 inches. Therefore, this beam is okay. So we've checked it for section modulus. We've checked it for moment of inertia. So in other words, we've checked the bending stress and we've checked the deflection. Both of those things are okay. The third thing, the thing you should check last, is the shear resistance. Shear rarely controls the design of a beam, so it's not something we typically need to worry about, but it is something that we should check in order to be thorough. So the maximum shear that is going to be applied to our beam is something, again, we can look the formula up for in Appendix H. So for a distributed load, the maximum V at it occurs at the supports is equal to the reaction force, which is just WL over 2. So let's write that down. WL over 2. In addition to that, we've got the shear force caused by the 2 point loads. So here, the reaction force is equal to the shear. That's going to be the maximum shear looking at the shear diagram, and that's just simply equal to P. So our W, again, was 1.050 kips per feet. And it's okay if I just leave this in feet because I can use the 24-foot length and those feet will cancel out and I'll just be left with kips. So I've got WL over 2 plus the point load. Let me remind myself what that was. That was 20 kips. So add that to 20 and we get 32.6 kips of shear occurring at the supports, the ends of this beam. So I'm going to have to stop this video here. I'm up against my 15-minute limit. But in the next video, we'll check to see, is our beam strong enough to resist 32.6 kips of shear?